Welcome to our LA SIGGRAPH September 9th Aerospace panel. I am Evelyn Harper, the chair of LA SIGGRAPH, which stands for Los Angeles Association for Computing Machinery, Special Interest Group on Computer Graphics, Professional Chapter. Let me introduce LA SIGGRAPH's producer, John Collins.
Well, thank you, Abilene. Here, stick with me for a second. I just wanted to thank you also for getting LA SIGGRAPH's EC to plan the whole year's worth of meetings. Please consider joining our chapter or donating at la.siggraph.org. And welcome to SIGGRAPH's Pioneers Perspective on Computer Graphics in Aerospace. LA SIGGRAPH is co-hosting this tonight with the SIGGRAPH Pioneers. With that, we have Ed Kramer, who is the current chair of the SIGGRAPH Pioneers. Ed was also the treasurer of LA SIGGRAPH in the 80s. Please give Ed a SIGGRAPH Pioneers welcome. Ed?
Yay. Hi, Joan. Thank you, everybody, for joining us tonight. This is a reprise of a panel that the Pioneers put on last February. And we've got all the original panelists back for round two. The Pioneers, for those of you who don't know, are a group of old timers from the computer graphics and interactive techniques industries. Anyone who has been working professionally in the industry for 20 years or more, which means that anybody who started in 2005 in this industry, you are now officially a pioneer, and you can actually join us. If you go online, you can look at SIGGRAPH Pioneers and track down how to join with membership. We just had a great conference. The Pioneers had a couple of amazing events. We always have a reception where we all get together, but we also had a featured speaker this year, Ed Catmull, who was the co-founder of Pixar Studios. And since it coincided with the 30th anniversary of the release of Toy Story in 1995, we had a special 30th anniversary screening for the conference. And Ed not only gave our featured speaker presentation about the making of Toy Story back then, but then he was also able to introduce this beautifully remastered print for all the conference attendees. We also had another speaker, Scott Ross, who was the co-founder of Digital Domain Studios. Scott has a book called Upstart, Digital Film Revolution, Managing the Unmanageable, about his years first at Industrial Light and Magic during The Abyss and Terminator 2, and then starting Digital Domain and winning Oscars for Titanic, What Dreams May Come. So Scott was a great speaker as well. So those two events are now live on the SIGGRAPH YouTube channel. Just go to Google and type in Scott Ross, SIGGRAPH 2025, or Ed Catmull, SIGGRAPH 2025, and you'll find them. And I think we're posting them also in the chat room. And with that, let's get to the reason you guys are here. I am going to introduce Dave Kasik, one of our founding pioneers, and in fact, the only human being on Earth who has attended every single SIGGRAPH conference since the very beginning in 1974. So Dave worked at Boeing, is emeritus computer graphics at Boeing. And why don't you take it away, introduce yourself, Dave, and then you can introduce the panelists.
So thank you, Ed, for pointing out that I really am old. I'm actually the only person who's been to every North American SIGGRAPH conference. I have not gone to any SIGGRAPH Asia, so it's okay. Anyway, at any rate, thanks to Abilene and Joan for arranging all this stuff and putting together a lovely agenda for the entire year. That's almost unheard of. To Leonard, Fran, and Ed for acting behind the scenes, Ed Lance, acting behind the scenes and making sure this entire thing runs smoothly. This is the picture that I like, is somebody who actually photoshopped hair out of me. It's a wonderful thing for Jean-Luc Picard. Anyway, I am a huge proponent for the use of visualization for all geometric and non-geometric data. It helps people understand. And I understand the implications of data growth, which is just getting worse since I retired a few years ago. This topic got onto the list of the pioneers because, and I do appreciate Joan and Abilene for inviting me to do this, for inviting us to do this. We believe that this is an educational opportunity to let you believe that computer graphics has had and continues to have an extraordinarily broad applicability, much beyond the scope of movies, games, etc. It's something that we use every day, but it turns out that aerospace, and there should be a number of aerospace people in the audience tonight because LA is an epicenter of the aerospace industry. Aerospace was one of the very first computer graphics adopters, both in interactive systems and in film. Some really neat things happened through the use of computer graphics. A Boeing person named William Fetter actually coined the term computer graphics in like 1960, and his claim to fame was making films of human models in trying to deal with cockpits and bridges on ships. And he did that by filming individual frames off of a plotter. It was dynamic work and done in the 1962, 63, 64 timeframe. The use of graphics is still expanding. There are marvelous things that the aerospace and automotive industries have done. And there are a number of references that are part of the slide set that you'll see. So aerospace turns out to be a broad term. And our panel consists of 4 different people. Roger Malina will start out. He is going to talk about graphics assisting astronomers to deal with the enormous amounts of data that they acquire from space. Pete Doenges from Sutherland, originally, is one of the pioneers in making technology work for simulations so that we could train pilots, astronauts, etc., in how to use complex systems. Julian Gomez has a more down-to-earth version of space because he was critical in working at JPL and NASA Ames in bringing scientific visualization to the front. And through the magic of being live on tape from Australia, Vladimir Karakusevic is going to talk about how Boeing is continuing to expand the use of computer graphics in a real live aerospace company. Vladimir was called away to meet with a minister of defense in Australia, so he's unable to join us live tonight. Roger's going to kick us off, Pete, Julian, and then Ed Kramer acting in Vladimir's stead. So that's the start. Roger, take it away.
I am here. Okay, so I'm Roger Malina, and I think since the word JPL has come up several times already, my father was Frank Malina. He was a member of the suicide squad that set up JPL. At the beginning of my career was working as the PI for a NASA satellite, the Extreme Ultraviolet Explorer, and I'll show you some of the computer graphics that came out of it. But I actually started computer graphics in the 1960s because my father used Meccano pieces and motors to hold a pen and draw things. So it was, I guess, not computer graphics, but Meccano graphics. But it really got me the idea that machines could help you understand things that the human eye couldn't do by itself. I went on to become a professional editor for MIT Press, the Leonardo Publications. I'll tell you a little bit about it. And now I'm endowed chair at UT Dallas, and we just set up last year an off-center for emergent studies, which obviously is a phenomenon very common in astrophysics and astronomy. How do spiral waves form in galaxies? And you have to use computer graphics. So as I mentioned, I was the PI of the Extreme Ultraviolet satellite. That's the thing we built. And that's the first images we got. And yes, there's a lot of sort of background noise, and so you have to use computer graphics to clean up the image. And we succeeded, and that's the maps of the stars that were hidden by the noise. You just adjust some knobs in the computer graphics, and we made the first map of the sky at this particular wavelength of light. So I've been involved with SIGGRAPH. I've been to some of the SIGGRAPH Asia events. I just wanted to mention one that I think was really meaningful for me. It was in 1990, and it was the work of art in post-mechanical reproduction. And a lot of computer graphics is mechanical. You just go from data to images and so on. But that was the beginning for me of the age of algorithmic art. And you could explore how you could use computers to twist images. And it was just really mind-opening how both artists, scientists, and engineers were in post-mechanical reproduction of data. And then to the extent that you made computer graphics as moving images, you could notice things you could not notice in the static image. It really was sort of a fork in the road for me. And I've then set up at UT Dallas an art science lab. I mentioned the Leonardo Journal at MIT Press. We were one of the amazing advocates of computer graphics in the arts and humanities. When the journal was founded in 1968, artists were told if you have to plug it in, it isn't art. And they were told artists are stupid, they don't know how to write, let the art critics do the writing. Well, we were able to prove otherwise. If you plug in a computer, you can make art that you can even sell. I won't get into the details. And artists may not write technical articles like computer graphics engineers, but they can express themselves clearly. And so we sort of pioneered a lot of technical writing by artists, and the journal is still published by MIT Press today. I just want to shift gears to one of the projects that we're working on at the moment. It's called Fred the Heretic. That's an AI-generated painting of him. And the database in the AI includes everything Fred Turner, a writer, has written over 83 years. He's published 40 books, many science fiction novels about Mars in particular, and a lot of poetry. So the database is very limited, and when you ask the AI a question, it can only use words and metaphors that the human being has used. AI cannot consult dictionaries or Wikipedia. And it cannot write in prose, it only replies in poetic verse. And it was a little bit of a shock to me that sometimes you can express facts using poetry rather than technical writing, which has been my forte. And then you can use computer graphics to make image of himself, make me look younger, that kind of stuff. Paul Fishwick, a computer scientist and computer graphics pioneer, I'll talk about him a little bit later, leads the development software. And what we've argued is that this software has very limited intelligence, only the things Fred has written in 83 years, but augmented intelligence is not always a good idea. If you know too much, you get paralyzed. And if you're too narrowly focused and don't know enough, you'll never solve a problem. So limited intelligence is sort of in between being an expert and being a generalist. Paul Fishwick in 2002 was so unhappy with the way computer graphics was developing The scientists and engineers didn't know how to use colors effectively and how different shapes attracted people's attention. And so we held a workshop in Germany and wrote an aesthetic computing manifesto, how you apply the way the brain perceives things to computing. And it's the typical, reverse engineering. Usually you use computers to make things and human beings watch them. And this is now the opposite direction. So it's not aesthetics as a design tool. It's more as a neuroscience tool. Anyway, we published the manifesto, and computer science and design and aesthetics. There are a lot of courses and books about it. So the Fred the Heretic, if you like, is an application of his manifesto 25 years ago. One thing that caught my attention as I've been discussing with my colleagues on the panel is when I started, the word computer graphics didn't exist. And it's sort of interesting if you go back at the history, the Jacquard loom was the first weaving machine where you could push buttons and it would make a tapestry of different colors. Well, that was a form of mechanized graphics. And of course, the Jacquard loom is often credited being one of the first computers. I lived through a period where it was called generative art, not computer graphics. I remember Harold Cohen, who was an expert at generating things by collaborating with the software. Information aesthetics became a popular word. How do you transmit ideas visually? I worked with the people at the Santa Fe Institute. I was on a funding agency in Spain when the artificial life, which obviously was dynamic animations, where things began simple and then slowly emerged and became more complicated and self-sustaining. Machine learning, of course, has spread. Raster graphics, information visualization. When I was researching this, I found Gaussian splatting. I don't know what it means. Anyway, so it was sort of interesting. I went to Google Ngrabs, and yes, indeed, when SIGGRAPH was invented, the word computer graphics didn't exist. It first appears in the literature in 1963 and hit a peak in 1985 in the usage in articles and books, and now it's dropping. I wonder if SIGGRAPH is going to change names. Then I played a little bit of a game with my AI. What words might be used for computer graphics in 2045? Well, synthetic media, because now it's so easy to combine in AR and VR, synthetic realities, synthetic media. So computer graphics is now part of 3 or 4-dimensional imaging. Neurographics, I was a little bit uncomfortable with this, but it turns out if you attach a mobile brain imaging cap to someone's brain, you can actually map not only the blood flow, but the idea flow in the brain. And I never thought of neurographics before AI suggested it to me. I've already mentioned immersive media. There are different names for it, but it is a little bit frightening how when you walk on the street, everybody's looking at their cell phone, and often you can turn the camera on and then you're seeing what you're seeing. And generative environments, obviously, I'll come to that in a minute. Perceptual synthesis. So I'm just going to mention a project we just started working on a few months ago. It's called Making IR with Purpose. If you know the science of complex systems in emergence, you know Maturana and Varella's concept of autopoiesis. Often in a complicated system, and we all know the software design between the cathedral and the bazaar if the software is too top down, it doesn't always do what you want it to do. And autopoiesis is how something suddenly emerges at the bottom of the software and then moves upwards. We have an alliance with a nonprofit called Making Art with Purpose. And so that's where the Making Eye with Purpose. And it's sort of interesting, just shifting ways of thinking. Making Art with Purpose was to convince people to be non-racist, non-sexist, etc. But how do we deal with AI? In the AI software literature, it's called AI alignment, where the software has to modify itself so that the readers agree with it. And AI is leading to a very different approach to computer graphics. Obviously, it can do the mechanics of it with no problem. And so in this Making Art with Purpose, we're collaborating with astrophysicists and aerospace professionals. We're using, and some of you will know, Hollemeyer, who was the head of DARPA for a while, worked at Texas Instruments that set up my university. And he had a very perspicacious way of helping focus on what they want to do. And so as part of that, we have a student working on creative marketing and AI, and it's just the beginning of the area. But I just want to mention, we do have a podcast platform, some of which is AI generated, called Creative Disturbance. And we've just been working on a project called Virtual Africa, because there are now 1 million students from Africa in Chinese and American and other universities outside of Africa. We use the terminology of desirably strange. You've got to think outside the box is the traditional way. Robert Root Bernstein talked about sparks of genius. You've got to somehow exercise all the parts of your brain to come up with new ideas. And we're working with Carol Christian at the Hubble Space Telescope. A few years ago, she pioneered the work of making computer graphics into tactile maps. So it was not visual. You had to touch it to figure out where a star was, or a dust cloud, or a spiral wave. And it was surprising that initially she started it for people that were visually impaired so they could understand computer graphics. But then people started noticing things with their fingers they didn't notice with their eyes. And, often roughness is seen as noise in vision, et cetera, et cetera. So I'm just going to stop there. You can hear my enthusiasm. That I'm part of multi-generational computer graphics that's changed names over the years. Thank you very much.
And now we move on to Pete Doenges for something quite different in terms of how Evans and Sutherland got into the simulation game. Pete, take it away.
Okay, let me see if I can rev this thing up. Thanks very much for joining our panel. I'm Pete Doenges with 33 years in visual simulation. I'm going to take you on an unlikely 56-year journey into the inception and evolution of computed real-time scene generation. The goal is training of vehicle operators to build skills while dealing with mistakes and failures. I luckily joined some pioneering technical visionaries who were searching for pivotal chances to start a business in visual simulation. I started at GE's Electronics Laboratory in Syracuse, New York in 1969. eLab was a vital incubator for 3D graphics R&D aimed at real-time visuals from the early 1960s. Work was innovative, demanding, fun, with great mentors and colleagues. Operator training sets a really high bar. Transfer of training from simulator to vehicle is possible if the fidelity and operator task loading are high enough to suspend disbelief. Visuals must deliver experiences that teach real tasks without negative cues. Simulator visuals make business sense when training flights or vehicle operations can be reduced. Here are the visionaries, Rod Rougelot and Bob Schumacher. I joined at GE. A number of you may know them. They aim to advance 3D technologies learn what users needed, build visuals, and do graphics R&D with proof of concept demos, probing at flashpoints to start a new business. Rod's group had years of foundational work in 3D graphics math, system architecture, and hardware software. A NASA JSC tie in the early 1960s led to an ELAB scene generator at NASA, driven by the Apollo program. ELAB's computed display research facility mocked up image generators and software with rendering and slow time to a film stand. I was busy with NASA work, IG and modeling studies, and a shuttle film. NASA Johnson's 10-year challenge to get men on the moon sparked a novel astronaut support visual from ELAB seen here. GE made a simulated graphical flight director, including textured ground surface for the Navy. This inspired NASA to ask ELAB for a lunar surface scene generator with motion cues over a large altitude range. NASA could study strategies for lunar approach and touchdown while saving fuel. In 1964, ELAB delivered this novel 3-channel electronic scene generator with textured surfaces in 4 nested levels of detail and 4,000-to-1 dynamic range. The ESG was expanded in 1967 to add a few 3D objects, including obstacles and a crater, plus a quadrilateral shadow found useful by the astronauts. Also shown here are an early flight director, docking of the LEM and command service module, plus an early shuttle simulator. Rod and Bob foresaw airline pilot training, real bread and butter for us. They met with the airlines to evaluate CDRF videos of airline daylight operations, night landings with runway lights and low visibility. The airlines didn't commit, saying ELAB had much to achieve. Yet takeoff and landing became a viable basis for a business in airline visuals. Dave and Ivan started ENS in 1968. They met Rod and Bob at NASA JSC to view scene generation as an inspiration for ENS visual simulation. By October 1972, Rod, Bob, and Ed Wild joined ENS to work on early products. I joined ENS in September '73. Graphics engineers with ENS contributed to these early visuals. By May 1973, ENS worked with KLM to deliver the first of several Nova views for airline training. I happened to develop and help develop the KR5 channel CT2 system for shipbridge R&D. A 3/4 circle display showed New York harbor scenes through simulator bridge windows. ENS took on this complex, first-of-a-kind daylight IG with huge challenges. I also worked on NovaView SP1, CT3, and CT4. Staff bonds we formed with hard work testified to this ENS family culture that I'll talk about more. Our early baptism by fire visuals pointed toward IG product foundations for decades to come. NovaView's point light simplicity, low cost, and quick ROI served high-value flight operations around airports and recurrent pilot training. CT5 and its lineage for high-end visuals leaped beyond the prior software-based scene management and image quality limited by the Watkins scanline algorithm of CT2 through CT4 systems. Here's NovaView SP1 at night dusk with sharp calligraphic light points, runway surface and markings, horizon glow, distant cityscape lights, limited 3D terminal depictions, and accurate fog effects available to simulate runway visual range. NovaView later stretched to accommodate daylight color scenes. NovaView SP3T here shows textured clouds and runway surfaces with and without fog. NovaView sold via rediffusion with their airline ties, and new CT5 architecture formulated in the latter 1970s could adapt to emerging applications. The airlines began widely adopting NovaView type visuals in pilot training. The military followed suit as CT5 and its derivatives stretched to meet stringent military demands. Sales growth ensued over a couple of decades with total sales around 1,000 systems and $1 billion. NovaView found a crucial kickstart due to limits of model board visuals. These offered detailed physical 3D models of airports and surroundings with high scene densities and visual cues. A large movable gantry with multiple channel cameras cruised over a brightly lit 3D model to allow and follow simulated aircraft movement. Yet models couldn't scale up for global airport operations, and upkeep of these models was complex. KLM Airlines joined ENS and Rediffusion in a fortuitous collaboration to serve new 747 simulators with visuals as jet fuel costs spiked under the 1973 oil embargo. KLM had experience with RSL's multi-channel camera model board visuals. Smart and visionary, KLM got curious about an ENS demo of a computed visual with airport runway lights. NovaView systems for KLM were then designed and first of 8 delivered in 6 months. The ROI, return on investment, in about 9 months on KLM simulators with NovaViews underscored this KLM article about fuel savings from cutting actual KLM training flights. The mold was cast as other airlines began making similar moves with Rediffusion and ENS. CT5 moved dramatic improvements in database management into special purpose hardware. High quality imagery and display processing of priority ordered polygons was teamed with this advanced scene management for very high scene densities. Anti-aliasing, supported by newly available memories, was based on area analysis of overlapping sub-pixel polygon fragments and smart filtering. CT5 used memory-intensive rendering to analyze polygon fragments interacting with each other within image areas. This so-called span processing pruned away hidden polygon fragments in front-to-back order with trivial rejection of later arrivals. Scalable channel expansion and scalable pixel formats incurred small processing increases. Visible polygon contributions to pixels that survive the span processing are subjected to 2-and-2 filtering here. Filter design supports energy conservation of polygon fragments as they move and phase shift across display pixels. Calming of image twinkle from missampled scenery achieved the goal to reduce miscuing of operators. CT5 architecture supported a variety of growing features that are listed here. A central innovation, though, was blending geospecific with geotypical scenery over large terrain areas with high image quality and special effects. And eventually sensors were also accommodated. Let's see, where have I gotten to here? Let's see. I wanted to talk a minute about this airport scene. Yeah, I think I've skipped a few. That was the problem. Okay. Yeah, here we go. This is an image of SeaTac Airport, which includes widespread texture and themals. I'm still off somewhere. Here we go. Themals mingling special local scene elements the pilot needs with generic 2D, 3D fill woven into the terrain. In the area of display systems, high-quality calligraphic and raster monitors were integrated with airline simulator optics to focus pilot attention at long distance. More sophisticated visual systems for the military, driving simulation, and others called for special projectors and monitors. Examples include edge-matched screen tiling projectors, hemispheric dome projectors, head-tracked area of interest insets, and special projectors gimbaled to display incoming targets critical to the pilot. Our display group grew a lot. Ultimate display challenges arose in domes for fighter aircraft. Mosaics of display channels were stitched together seamlessly for contiguous medium resolution large area scenery. Head-tracked high resolution area of interest insets and target projectors for eye-limited operations set new standards. Procurement specs for burgeoning visual applications we had to deal with beyond the airlines grew increasingly demanding and complex. Bid estimating, starting with our baseline visual products, had to account for system integration with team members, host computers, configuring view channels, database size and focus, special scene features, advanced displays, and more. Our proposal work grew into extensive application and systems engineering with broad organizational involvement in project planning. I touched on family culture a while ago, and I wanted to really emphasize that here. Dave Evans grounded family culture in ENS and shaped staff additions. Rod and Bob embodied these values deeply and encouraged a kind of family support through thick and thin. Influx of U of U graphics research, plus excellent, technically sharp, diverse new employees, some with international backgrounds, facilitated our interfaces around the globe. A flat organization feeling fostered lateral communication, and it really worked. Annual ENS reunions reflect our persistent family culture. A couple of weeks ago in Salt Lake City, I joined ENS folks who'd retired years ago and still come to reunite and swap stories. It's a rare and wonderful thing, and relationships are rich. Now we'll kind of address where we've gotten to over the first couple decades of this story. I left ENS in 2002, so I'll look forward to a larger playing field when I'm not actually an insider with the industry now. Based on my web research, let's examine what we achieved by 2000, changes in the industry since then, and challenges and promise out ahead. As shown, we've made huge strides toward realizing the quests in my earlier slide. These are scene complexity and density, mission focus, geospecificity, no jaggies image quality, varied displays, good physics, no missed frame weights, and expanding application. In the latter 1990s, harbingers of change and disruptive technology began to appear. I attended with great delight the Computer Game Developers Conference in 1996, as well as later ones. I discovered a palpable revolution taking off. 3D game designers were hungry to seed wild innovation toward movie CG with PC 3D accelerators. Trailers and overflow parking premiered hot new 3D chips. Striking to me was that game developers could now exploit the boosts in 3D graphics hardware with software API abstraction layers to build apps. Later, visual simulation firms began to make light IGs with PC 3D graphical processing units, or GPUs. After I left ENS, proprietary IGs continued forward to excel with ENS and its competitors. Yet some simulator primes had started making their own IGs. Some IG firms were absorbed in aerospace consolidations, with primes adding critical value via their application focus. Here we see kind of the rest of the story, with Collins Aerospace taking up ENS simulation and CAE making in-house visuals. As IGs matured, increasingly common were PC 3D GPUs and software accelerator tools to build applications. Here we see the Collins EP8100 image generator, their top performer, with proprietary ingredients. Their lineup more recently added the Arcus Visual, a hybrid IG that exploits GPUs and the Epic Games Unreal Engine, a development kit for gamer apps with GPU optimizations plus database and scenario tools. This is the CAE Prodigy Visual, a scalable IG built on NVIDIA GPUs, Unreal Engine again, and application refinements developed by CAE for the airlines and military. Note that global shadow rendering seems to echo use of GPUs and gamer-inspired tools. Looking to some more companies, here's GE Daytona, the product company I worked with for a time, continued under new ownership of Lockheed Martin. Lockheed later left proprietary IG work, acquired rights to Microsoft Flight Sim X, and evolved that into Lockheed's Prepare 3D. This is a system development environment that can use Echelon technology IGs partnered with NVIDIA GPUs. Flight Safety, with their long-standing vital visuals, is tapping into Unreal Engine and GPUs now. Here's a sample of the Echelon synthetic reality system that can integrate with Lockheed Martin's Prepare 3D. With these examples, my sense is that earlier IG firms are evolving into building on COTS GPUs, adding value with sharp application focus, scenarios, models, special effects, system integration, and so on. As outlined here, the sky might seem the limit in pointing IG evolution toward gamer or movie realism. Yet training is a business focused on expanding applications around the globe. Their successes, from high school classrooms to large institutional training, depend on the economics of enough realism for valid transfer of training and not fluff. A GPU system is not a training IG without high visual qualities. Looking to next enabling technologies, I can't see inside simulation IG and training firms today to see how they're reaching for the stars. I think about the qualities and realism that ENS simulation always sought to improve. The issues in the first half of this slide give me pause about convergence of training IGs and extreme PC games. One sure priority is evolving beyond today's IG or GPU capacities for more unscalable polygons, texels, themals, pixels, great visual and sensor physics, and no blink image quality, even as scene elements get highly entangled. Technologies that enhance accelerator kits for making simulation apps can exploit GPUs more systematically and broaden app development. Modern training device firms are homes to subject matter physics and user experts, and they all need application developer tools. Finally, and there's quite a bit more here than I can take time to explain, AI has infiltrated GPU features with deep learning techniques for database and rendering optimizations that aim to multiply GPU effectiveness. Our first example is driving simulation for tractor trucks and driver CDLs. I spent recent weeks excitedly on the web discovering the abundance of training simulation firms now operating globally, and I saw simulator market studies predicting unheard of sales forecasts for trainers. Firms are using PC inbuilt 3D or GPU graphics for multi-channel visuals in all sorts of domain and cost-focused applications. These and subsequent images are real physical trainer families offered by companies who have proven fielded systems and even corporate user partnerships. The commercial and private aviation sectors are now served up and down the spectrum by firms positioning specific trainers under FAA rules. If you look at the first few lines there, it's interesting to see the carve-outs for allowed qualified simulator time. And lastly, heavy equipment training, just another example. Such trainer products and services cover many vehicles today. There's specific controls, configurable cabs, roads, work settings, situations, equipment, tools, payloads, even rocks and dirt with underlying material physics, usage justifications, and a lot more. The variety of trainers and firms just simply boggles me. So I can only say the future of VisSim sure looks really bright to me, and those that are in it are surely having fun. And that's it.
Thank you, Pete. And so now we'll turn it over to Julian. If you'd go ahead and share your screen, Julian, you're on.
So I'm going to present a somewhat more historical narrative of visualization at NASA and talk about its progression from what we could do back in the 70s to what we can do now. So my background at NASA, I was part of one of the original members of the great JPL graphics lab, and then Bob Holzman, the founder, and Jim Blinn sent me off to get my PhD. Came back to NASA, but this time at the Ames Research Center at the height of scientific visualization, and then came back again 15 years later as NASA started getting into knowledge management. My dad was also an old NASA denizen post-war for the next 25 years, so he got to see the transition from NACA to NASA. One thing I should mention, I've never been a NASA employee. I've always been a contractor. In fact, most of the people you see at NASA centers are contractors. First at Caltech, California Institute of Technology, who operates JPL, and then USRA, the University Space Research Association, who provides many of the scientists at NASA Ames. So in the beginning, by which I mean the 70s, there was people drawing pictures using paints and colors and all that. And if you needed animations, it was done with cell animation, just like Disney, Warner Brothers, etc. Along came COM, which Dave Kasik got to experience back in the 60s. COM was fairly limited, and of course it was a very batch process, by which I mean you did a whole bunch of calculations, and a few days later you got to see the result. Then in the late 70s, the JPL graphics lab came along. We started with an ES picture system and ENS frame buffer. So there weren't many installations like this, but it gave us the ability to do real-time, interactive graphics, vector graphics, and then through Jim's rendering to do the shaded graphics. Mission movies to show the public what was happening in a space mission were an established thing at NASA. But as I said, those were done by hand through cell animation or other kinds of stop frame animation. So the idea was, what could we do if we were using computers to render images, well, we needed to be able to render images. Thus, Jim came along. And it wasn't just the PR movies that were released to the public. There are lots and lots of missions that get proposed and they don't get approved or they don't get funded by Congress. So many more frames were rendered than you got out to the public. We also did other mission support activities, for example, telemetry visualization for Voyager, and I'll talk about that in more detail in a few minutes. What's neat about doing movies is you can see what you can't see, right? When you're watching a movie about a space mission, there's nobody out there with a camera to show you what's going on. There's only the spacecraft, and you can only get the points of view from the instruments on the spacecraft. Of course, with CGI, we can generate what we want to see from a different point of view. We can render things that can't possibly be seen. For example, Voyager 1 discovered volcanoes on, was it Ganymede or Io? Shoot, I'd have to check that detail, but that was not something that was anticipated. And so the instrumentation on Voyager 1 and 2 wasn't really oriented towards seeing that, but we could get the data and do a visualization of it. All the Jovian planets have rings, it turns out. Until Voyager came along, it had been thought only Saturn had rings. And the number of moons. It's incredible how many moons. I mean, back in Galileo's time, Jupiter had 4 moons. Later on, we knew that it had a couple dozen. Now we know Saturn has hundreds of moons, so there's a lot of them. And with the spacecraft sending out there, picking up data, we can now visualize what those moons look like. Pioneer Venus, which preceded the Soviet Venera, used side-looking radar to image the surface of Venus, and I constructed a 3D visualization of the surface of Venus using that data. I turned that technology upside down and did a visualization of the Monterey Bay seafloor using side-looking sonar data. Now, I was going to mention a couple of things that are very important about visualization, not just the things that you can't see, but the things that are hard to see without visualization. So to show you, there's the Voyager spacecraft. And as you can see, there's lots of instruments on it. And this is a nice rendering from NASA about what the spacecraft looks like. And here's the main the primary science platform on Voyager. And those are a whole bunch of instruments and different spectrums of energy. And what an instrument sees is it's on the planet or the body is its footprint. For example, here are a few frames from the Voyager Saturn encounter movie, which show some footprints of different instruments. So what was the thing about this? Is the visualization is important is that Voyager's missions were planned starting back in the late 60s. Any deep space mission you see that NASA sends off has been in the works for 10 years at least. And of course, back in the 60s, your output was pretty much only printouts and maybe some comm movies. But what's the sequencing, what the instruments were going to be doing when during the planetary encounters had been analyzed for a long time. Now, the rendered movies that you saw of Voyager 1, Voyager and 1 and 2, Jupiter, Saturn, all the encounter movies took a long time to render because back in the 70s and 80s, it was 10 to 20 minutes per frame. But the simulator that Jim wrote for the picture system too was real time, interactive, so that you could twist dials and see what the instruments were doing as they swiveled around on the science platform. And the Charlie Colhase was the mission sequence director for Voyager, and he was screwing around one day, well, not screwing around, he was investigating the encounter sequencing for the Voyager 1 Jupiter encounter early in 1979. And eventually discovered that one of the instruments was obstructing one of the other instruments during the encounter. And the thing about a planetary encounter is that there's only one chance. There's no pause, there's no reset, there's no redo, there's no undo. It's going to happen once and that's it. And if something goes wrong, there's no second chance. So here he is discovering that during the Voyager 1 Jupiter encounters, one of the instruments is going to be obstructed. Now, luckily, this was a few months before the encounter, so they reprogrammed the sequence so that the obstruction didn't happen. But you think about a decade of printouts, just millions and millions of pages, and all of the mental visualization process that people had gone through for the Voyager 1 Jupiter encounter. And nobody had noticed this. It wasn't until Charlie was using interactive 3D graphics that he was able to discover this. Another thing that happened with Voyager is they had a problem and they were trying to figure out what it is. And one thing about spacecraft is that whatever happened a long time ago. So when you get telemetry from a spacecraft, it happened quite a while ago. And we now know that the Voyagers are quite a light distance away from here. Even at the Jupiter encounter, I think it was around 20 minutes. I don't remember now, it's fuzzy. So the telemetry that was coming down was old, and any new commands that had to go back to the spacecraft would suffer the same lag. So it was quite a bit of round trip time. So the analyzing had to be done it was a very offline and mental process. And to make it even more fun, when something happens on the spacecraft, it's what they call spacecraft event time. By the time it gets to Earth is what they call Earth receive time. And there was another time lag for the lag between the DSN receiving station, which might be on the other side of the Earth, to JPL. And yeah, light travels 7 times around the Earth in 1 second, but that's 140 milliseconds, and that can be pretty significant in computer times. So eventually I wrote a telemetry visualizer for Voyager. And the funny thing is, it turns out that was the official justification for creating the JPL graphics lab. It was Voyager telemetry visualization. It wasn't to do mission movies, it was to do an engineering function. But it worked out very well because I had to learn about things like SCE, spacecraft event time, ERT, Earth receive time, etc., in order to visualize the data. But then the engineers started using it because the visualization of the data was way, way better than those millions of pages of printout. One day, one of the engineers was down there. They were having some problem with Voyager 1. He was looking at it, and I was sitting at the other desk, and I heard him say, "Look at that." So I turned around and looked, and there were a bunch of lines on the screen. And I didn't say anything. He pointed and said, "See there. I wonder if that's it. It looks there might be a short circuit." So I kept looking, didn't say anything, because, of course, I didn't understand it. And then he picked up his notes and left, and it turned out that they were able to send a workaround to Voyager because of the problem they were having. Now, to him, he knew what the lines meant. He didn't know how to put lines on a screen, but he knew what they meant and was able to understand and rectify the problem that way. And me, I knew how to put lines on a screen, but I didn't know what they meant. So that worked out pretty well. Now, at the JPL Graphics Lab, we did other things, and I'm sure many people have probably seen much of it. One of the early ones was NBC was going to do a series about NASA spin-off technologies called Escape Velocity, and they needed computer graphics in order to do the visualization, and of course got sent to the JPL Graphics Lab. So I did this lead-in, but the series never got aired. Later on, there was a more significant series that probably most of the people on this webinar have seen, and these are, now old favorites in the scientific community. The best way to view the information about this is Jim's website, because he's done a significant amount of cataloging of the work that he's done. And in terms of non-space mission viz, then no, don't forget David M. He used to come in late in the afternoon, early in the evening, and work through the night when we had all gone home. He couldn't do that when we were rendering, of course, because rendering was an all-night process. But that was definitely not a space mission activity, although David had a hard badge. He was part of the lab. There is more coming about the history of the JPL Graphics Lab, because there were quite a few projects we did there, not just planetary encounters. There used to be a website. This has now been moved to the Computer Graphics History Institute. Postgraduate school, I went back to NASA Ames, and by the 80s, computational physics had become one of the hot things, and this was the driving force for a lot of scientific visualization. And the reason that this was possible was because of supercomputers, massive amounts of flops becoming available. You think about the 70s when everybody did computer graphics on some kind of PDP-11, which didn't even have 1 megaflop. And now there were Crays and other kinds of computers that turned out to do megaflops, and not too long that turned it to gigaflops, and eventually the scientists were able to push it to teraflops. This one paper in CACM is a good summary of what was happening at the advent of this movement. NASA identified Ames Research Center as their center for computational methods, and especially focused around CFD, because the intent was to start replacing the wind tunnels with computational methods. NASA, Ames Research Center and Langley Research Center were the primary sites with wind tunnels. Ames had 22 of them originally. It's much, much less than that now. But because the supercomputers cost so much money, a Cray 2 cost Ames $17 million in early 1980s dollars, and of course required a floor and an outside air conditioning plant. And this is just for one supercomputer. So part of the effort was not only to investigate what kinds of different supercomputers, but whether algorithms could be moved down to smaller scale supercomputers. And if you heard the name Sequent or Hypercube, this is the category they were in. I wanted to call the smaller supercomputers Crayolas, but there was sort of a trademark problem with that, so I called them Crayettes instead. The main force behind doing CFD was the Navier-Stokes equations for modeling fluid flow. And if you want something to make you run screaming in terror, forget the Halloween movies. Try the Navier-Stokes equations. You couldn't just calculate all these massive amounts of numbers. They had to be visualized somehow. And so this is mid-80s, so that led to SGIs all over the place, plus high bandwidth channels between the supercomputers, their peripheral computers, and the SGIs. Ames developed their own scientific visualization system called Plot3D, written by Peter Buning, and it was a Fortran package. But outside of NASA, we were seeing SciViz authoring systems which were typically built on a data flow architecture, like APE from Ohio State University, AVS from Stardent, arguably FIGS. It didn't seem to achieve the same amount of popularity as APE and AVS. And the thing about APE and AVS is they were intended to do data flow programming of scientific visualization on the Crayon class computers. So let's see. After a few years of doing CFD, fluid dynamics, and computational chemistry, I got lured out by business and went to Macromind. After the demise of Sun Microsystems graphics division, I went back to Ames, this time to do knowledge visualization. And by this point, NASA was moving to how do we handle these really complex, massively complex systems like the Space Shuttle Orbiter. And I'll be using the term orbiter because this refers to the part that actually went into space. STS, the Space Transportation System, includes the collection of the solid rocket boosters and the main booster, which got ejected, came back to Earth. Only the orbiter went into space and went into orbiter, thus the orbiter. Very complex system, over 2 million parts in it. When the SIGGRAPH publication talks about how we were approaching the problem, it was a part of an overall program at NASA called Engineering for Complex Systems, which dealt with this issue. And the idea was to use virtual vehicles in order to model the real vehicles. Today, this is called digital twin, but back then we were calling it modeling or simulation. So Digital Shuttle was a collection of everything known about the orbiter. And because of the way NASA works, what they knew was scattered all over the US and Canada. The arm was made in Canada. Some things were done at Marshall Space Flight Center, some in Cleveland at Glenn, what's now called Glenn. And if you needed something, it wasn't easy to try and get it. It could take you a while. When the shuttle fleet was grounded back in the late 1990s because of a fuel leak problem, they couldn't find the drawings for the flow liners, which controlled the fuel. And it was because stuff was scattered all over, and that's when they realized complex engineering, complex systems needs to be a program, and one of the aspects of it needs to be the digital shuttle. But it was a knowledge management system. It wasn't just engineering drawings. It was everything that was known about the systems. So here's some examples of systems, right? For an orbiter, for a space vehicle, you have at least these four. This is not a taxonomy. This is just a few example categories. In fact, the actual orbiter taxonomy was quite different. Now, for any one of these views, you have at least these logical, schematic, and visual. You think about electrical systems, and for any one of those, they can come in multiple versions, and they're all connected to each other. And if you're trying to navigate it, this turns into a huge problem because you might have 12 windows or 12 panels around while you're trying to understand how things work in this very complex system. this is what I called simultaneous multiple parallel navigation, because at any given point, your navigation had to be the same in all of them. It was in multiple different viewpoints, and it had to be navigating through them all in parallel. So it was pretty clear that VR was the only way that this was going to handle it. And this was what the research was going on in the early aughts as we worked on digital shuttle. And it turned out that it was actually implementing the scientist workbench, which was a conceptual thing from NASA back in the 80s. That was written when it wasn't possible to do. So it's just a conceptual thing. As we started putting together the digital shuttle, there was lots of stuff to work on. There's an old joke about how the documentation of the orbiter outweighs the orbiter. It wasn't a joke. There were over 2 million engineering drawings just for the orbiter. And they were on paper. They were in the shuttle drawing system. They'd all been digitized. And they all had, lots of them had handwritten notes because, as I said, design went back to the 60s. The handwritten notes, of course, were critical information. So we went through and we just scanned. Well, we didn't get to scan everything because of the president, but back then, Bush, I mean, not the current one. We scanned the handwritten notes on the basis that a false positive was better than a false negative. And all of these things would then get entered into the semantic part of the database, the knowledge base. I did one where the shuttle photograph system was, again, millions of photographs. And I did a thing where I'd put up a photograph on the screen, and then you'd manipulate a 3D model of the orbiter to match what the photo showed. And from that, I could back solve to pretty approximately where the camera was when the photograph was taken. Because remember, these photographs started in the 70s when there was no 3D location data for a camera. Also, let's see, visualizing different parts of the orbiter and tracking that back to the documentation for that. A simple example would be looking at an avionics stack and going back to what's the bill of materials for that avionics stack, and from that back to the manufacturers, et cetera. This one I want to throw in because even though it's not digital shuttle, this was for the ISS, the International Space Station. This is a sample of the fault detection network, and yet all the colors and mean something about what kind of fault detector it is, and the idea was to show the connections because, as it turned out, the fault detection network is a massive data flow network. This was done using the Xerox star tree algorithm, and this diagram was actually interactive, so you could slide nodes around and see how they connected to each other. So much of this was documented, of course, in NASA. It's now historical because the STS was EOL. Space Transportation System was end-of-lifed in 2004 by President Bush. So much of this stuff is historical if you can find it. The digital shuttle was documented at the NASA Virtual Ironbird workshop, which was lost and recently recovered. That used to be in its own website, and it's also moved to the Computer Graphics History Institute. So in the future, what's happening for NASA? Well, computational methods. And it's not just NASA, this is happening everywhere. You think of bioinformatics, which didn't exist all that long time ago. It's all been enabled by serious performance computers, serious performance in computers. At SIGGRAPH 23, found it interesting that both Smith and Whitted were on a panel about the 50 years of computer graphics, and both of them took the approach of measuring increases in performance of graphics chips and how that corresponded with increases in what you're able to do with graphics. So that was an interesting panel there. Not just that, but CAD/CAM PLM for engineering is just so much more sophisticated than it used to be. And I want to stress that computational methods are just coming out all over because, as I said, Ames used to have 22 wind tunnels. When I checked a few years ago, they were down to 6 because computational methods had replaced so many of them. Oh, and yeah, interdisciplinary, we have to stop thinking in silos. It's not just CAD, and it's not just fluid simulation. It's all of these are linked to each other. And that was part of what we were starting to get at with the digital shuttle knowledge base. But what is the future of visualization at NASA? Well, that's the real question we have had come out in the last 6 months. So I'm not going to hazard a guess or any comments because that verges into ranting and I'm over my time limit anyway.
Thank you, Julian. That was really very interesting. And we're going to get to one last presentation, as I said, live on tape from Ed Kramer's office. First, I'll add a little bit that Leonard told us about the Voyager discovered Io. So we've got that fact straightened out for you, Julian. As we keep going through these presentations, I want you to all think about the complexity that we're dealing with in aerospace and other disciplines and map that back to the past, where a lot of the work was done in building and design with stones and other things, and how people succeeded in building complex systems with slave labor, let's be real. And now we're dealing with even more complex systems, and computer graphics is a really big deal in understanding that complex data. So with that, I'll turn it over to you, Ed Kramer, and Vladimir. Thank you so much.
Hey, everyone. I'll try to summarize. A lot of people said a lot of things that we already covered from Boeing perspective, so you did the good thing for me. What I want to share with you a little bit is what we did and where I sit, where Dave used to sit at Boeing, fellow at Boeing. I mean, 35 years of aerospace, and let's say 30 years of visualization all over the world, different companies, different efforts. But I want to share with you a few photos first, and then I'll quickly go through my slides. Photo number one, this is where we started as a company. If you ever touched the analog computer, well, Boeing was doing it in the 40s. And that was the that was the starting point before we went into the CG and visualization. Second one that I painfully am aware of it is, if you guys ever had to plot something of scale, is how it looked, the Gerber plotter. We had them for years. We still have printouts from these plotters that we're still using, unfortunately. This was a mess, but it was the high end. And especially because of Dave, I'm showing the next photo. And this is actually the Intergraph CAD workstation from the 80s. I encountered them, not at Boeing, outside. And the lady whose choice of clothes, I think, influenced later Star Trek, Captain Picard, I guess. It's the same colors, Dave, so I didn't know that we were pioneers in that area too. These are all the areas where Boeing was pioneering, and thanks to Dave, I have the opportunity to share with you, because Boeing is very stingy nowadays in sharing any kind of IP. So I'm leveraging something that is a little bit older. Maybe some of you, definitely one on the call, have seen that next to Dave. And a lot of us were or still are involved with all these elements that you maybe didn't know that more or less started at Boeing, or Boeing was heavily involved in creating those things. I don't want to go through every one of them. I'm currently still involved with, let's say, the last 5 items that we're still taking a look into and developing capabilities. Let me go to the next slide. As you know, guys, or you don't know, the term computer graphics, we claim it's coined at Boeing. Others are saying it's different, but we still stand behind it because we have the record to prove that, right? And human model was the first application of computer graphics. I know that the originals of this visuals are in Victoria and Albert Museum, if I recall well, in London. And I was very proud to see them shown to everyone a few years ago. Fractal animation, you guys, I'm not sure if you're aware of, but they can go into details about Lauren Carpenter and Vol Libre. And we know the history after that with Star Trek movie number 2, The Wrath of Khan, and then later Lauren's contribution to computer graphics that was significant, that started at Boeing. Augmented reality, the term got coined at Boeing, and lo and behold, is one of the first augmented reality devices still sits in my lab, in our lab actually, in Everett near Seattle. The pioneers were at Boeing, and we're still using it in many places across the factory. But people tend to forget a lot of that industrial use started with us. Massive level visualization. As you can see, Dave was pioneering that. We continued to work in that space, and we're always 3 steps ahead of not only the competition in aerospace world, but also the likes of Siemens, Dassault Systems, PTC, and other companies that are trying to catch up with us in industrial use of this concept. So as you can see, multiple things developed at Boeing. We are still continuing in that direction. And, you know, like from the perspective of highly complex products and huge amount of data, we're trying to leverage visualization. Maybe in the future, it'll be other senses that people like Roger was showing to us. And we're trying to make sense out of this complex visual data sets. Unfortunately, no vendor is capable of handling that for us. So we have to develop our own capabilities. And that's why we're constantly in a position to push the state of the art and to try to achieve things that make sense for us. We have not anymore dozens, but hundreds of use cases that are containing a visualization of both geometry and non-geometry data. Typical case, very simplified, is where you see the geometry of a product, where you see the general info. This is the, in this case, is tolerance info and the product structure. This is still the essence of our visualization, which is maybe a little bit dry comparing to the really nice visualizations that we've seen before, but is essential for us to design, produce, and support our line of products in aerospace. High-end versus low-end, what does it mean? In our case, it's really important to be able to scale things from very small scale to very large scale and back to a very small scale. Because of that, we developed some capabilities that, as I said, are still leading in the visualization domain, that are capable to handle the data and to jump between small and large scale. Today, it's easy if you're using Google Maps or Google Earth, which is even better, for example, to try to do that, you know, like zoom in on the house on the Earth, then zoom out to the whole Earth and zoom back to the house on Earth. Well, we were doing that since the early 90s, and on a very similar original case, which was going from, I think, scale, remind me if I'm correct, from the scale of a house on Earth to the whole solar system and back to the house on Earth, which we generated as a tool called Fly Through at the time. And now, after 20 plus years, we're still working on that concept. Standard visual applications, as I'm showing, you all know Adobe Reader and different browsers that are sitting in this very low scale. And then you have typical engineering visualization tool that come from some of vendors on the commercial market. And then we are handling data of, like, it shows here 1 billion, but I can tell you now it's more than 15 to 20 billion polygons easily in real time. What the low-end visualization here for us means is a very easy way to show some tasks depending on use case, and I'll demonstrate the visualization. What does it mean? It's the parts information management system that shows to our customers or our supplier management or support and services to easily visualize some parts and their context from the perspective of an assembly or a bigger airplane. Then we have something called engineering information delivery. This is the system that carries all our manual content and technical data that we share with our customers, whether it's defense or commercial or space. We also help show floor work instructions. That means something that used to be very advanced, that now it's moving in the realm of extended or virtual reality or augmented reality or mixed reality, are the shop floor 3D work instructions. The easiest to explain it is IKEA instructions that are fully, IKEA-like instructions that are fully 3D and that are available to every mechanic either on the shop floor or outside in front of the product. And they can leverage any type of HMD to access that type of data. Trying to rush through this. High-end visualization is a little bit different. We're expecting to manipulate 10 plus billion of polygons at 50 hertz or faster. So preferably higher if you're using HMDs, so you really avoid cyber sickness that Chris Esposito, who's here attending, was researching. And we were getting those high numbers with a good reason that we wanted to be able to put people inside the product or inside the production system without getting sick, right? And to be able to interact with all that data. As you can see, product structure means 800,000 plus parts or millions and millions of instances, and then selection and feedback at a very short time. So we're easily achieving that on multiple hardware platforms, starting with iPads, tablets, low-end computers, because of the some tricks in development. I won't go into that. And there are multiple use cases, as you can see. I don't want to go through the details, but it's across all the life cycle of all the gamut of products that we're having in space products, aviation products, etc. These are the typical views of this high scale. Some images from this very large scale products that we use. We can show the whole airplane with all the details. Notice please that rendering is done not with the real color of parts. Everything could be just purely gray or greenish. We're insisting on giving the random different colors so the important pieces are visibly distinctive, so we know what we're seeing in front of us. We're using it, as you can see, we can visualize the whole airplane or a fleet of airplanes if you want to, with the same hardware that I was describing before. We don't need any super high power computing or anything like that for those visualizations. And we're using that heavily, for example, for something called product data reviews, in which we're basically looking how to put things together, how to produce them, how to put them together, whether everything fits together. And these are the massive use cases, and I'm just using one because of the scale. So what is in general important from the perspective of aerospace industry is being able to visualize large quantity of data at very high speed, and to be able to switch between different scales. Typically, that type of capability doesn't exist in the commercial off-the-shelf world, so you have to develop it on your own. And I think we're still successful in that. That, in addition to everything you previous panelists were saying, I think gives you a little bit of the flavor of high-end industrial use of visualization that, as I shown you, started in late 40s with analog computers.
And that is the end of the formal presentations. And now I'll go to the questions that have been asked through Q&A. Please feel free to add some more because we have about another 35, 40 minutes to be able to chit chat amongst ourselves and answer some of the questions that have been posed by the audience. I'll start with the infamous anonymous attendee question. What effect do drones have on our various forms of work? I get to answer from the Boeing world, but Pete, what do you think from the simulation business?
I don't know. It's probably all secret.
It's probably all secret.
I haven't a clue. No, obviously, at least from what's published, drone imaging and drone training are a potentially big deal. And I can imagine trainers, but I'm sure that's not revealed to the rest of us. I don't know.
Well, I certainly can see the training aspect, but there's also one of the things that we're finding is that there's a huge intersection, huge overlap between computer vision and computer graphics. People in the computer graphics world have a tendency to tend to not want to deal with image generators. It goes to you can see it manifest in autonomous vehicles. which drones can be, or in the operation of said vehicles. They generate a lot of data in real time. Julian, do you see any overlap with what happened with what NASA had to do and what's going on with the autonomous vehicles represented by drones?
Absolutely. I've noticed in the last 15 years, NASA has had to turn a lot more to earth sciences, presumably to keep their funding going. And of course, as they go into earth sciences, then drones become a bigger and bigger part of remote sensing. So.
Okay, so if Mr. or Ms. Autonomous has any follow-up questions, please ask, and we'll figure out what's going on with that. We'll try to do our best in answering these things. Andrew Gerard, who's probably in the UK waiting to go to sleep.
Oh, one more note.
Yes,
I want to point out that NASA flew a helicopter on Mars. I mean, for
right.
Pete's sake, mankind put an aircraft on another planet and flew it around. It's like, talk about drone technology. So.
That's okay, and you can get all your real estate listings through drone pictures now too, because they'll do overviews, take images, all sorts of interesting applications. Anyway, Andrew asks, atmospheric effects have been a recent focus of gaming with a reference, including lighting effects. I'm curious when and how that was implemented in professional flight simulators.
Well, if I can speak,
You
Dave.
better.
Yeah, we were doing atmospherics and special shading and reflections and shadows and other things in very economical ways that were not ray tracing. But it was really important to have the atmospherics and the variable lighting portrayed in some focused areas of the simulation where it really mattered to the operator or the pilot. So I'm not sure I'm answering the question, but
well, you are partially.
We couldn't afford real-time ray tracing and all of that is possible. And in games, sometimes frame rates are compromised in order to turn on much more robust ray tracing or shadowing or atmospheric effects, fog, whatever. But in a world like ours, where we've got to make every frame in a 60th of a second, if we have a programmable GPU, for instance, where we could focus on the kind of imperatives I talked about during my remarks, or chase some ultra realistic gamer effects that I'm seeing today, rampantly around the internet, there may be a real crunch in trading off the generality of ray tracing or whatever it takes to get that gamer effect in a local environment against a sustaining frame rate. So I think one of the challenges from my point of view, from the simulation industry's standpoint, is if GPUs, as I mentioned in my remarks, seem to be kind of taking over a lot of aspects of visual simulation, the people who build those applications, at least from the standpoint of training imperatives, have got to make frame rate and make all of those special API invoked special effects that are possible with GPUs fit within a frame time.
So I'll make a quick comment about that. I'm answering a question to Roger. So Roger, I'll ask a question that is for the whole panel, and then we'll let you go, because this is one of those cases where time zones are not working to our advantage, and sometimes you just have to let people go.
Well, plus I have to teach tomorrow morning, so.
I know. Well, it'd be good for you to be awake while you're teaching, Roger. So I'll make another comment about the special effects for the simulators, Pete. And was there special hardware? How did ENS actually get those special effects included in the scenes? Because that's a really good trick that you guys played.
Yeah, I mean, we had basic Phong shading and some other kinds of shading available in the system. We tended to render polygons in some kind of very carefully orchestrated manner, so that we could solve the anti-aliasing and high quality prioritization of objects for visual occlusion in the fashion that I talked about. But we did have Phong shaders and could deploy inside the rendering engine limited invocations of special effects that are used rampantly in games, but which we cannot afford to generalize, at least with the older architectures I work with. It's harder to generalize those special effects over the entire huge models that you saw in some of those images that were so geospecific during my talk. So in order to get,
how did you model how did you model fog or specify fog or specify other atmospheric effects, clouds? How are those defined?
fog was all an issue from the operator's point of view, of course. So in the most rudimentary NOVA views you saw in that in my remarks, the very first fog rollouts were simply using distance, along the path to polygons to figure out how far away things were, and all of the fogging effects on runways were very precisely calibrated by measuring, distances and applying appropriate results in blending the object and the fog that's in between you and the objects. Later on, we did special kinds of fogging, including ground fog layers, which are very important to takeoff and landing operations. And later on, focused fog cells and cloud cells, which you saw, I think, in several of my pictures, where a local particle system or a local fog bank, even blown dirt under a helicopter, which you'll see in demos on the web, is achieved with objects out in the scene that are evaluated along view lines in order to get the amount of fogging that's needed. And so I don't know whether that's answering the question, but
well, that comes closer. So
and everything was sparingly applied, to get just.
Can I jump in on that?
yeah, sure.
Okay, so I work with a colleague here at UT Dallas called Jeff Price, and he's been developing what's often called digital twins. The easy example, he had his students film a whole building that our school is in, and then you can light a fire and see how it spreads in a virtual building. And it's sort of, it makes you think. And then about 6 months ago, he got a very multi-million-dollar grant from the FAA to do exactly what you were talking about, which is, you can simulate airports, but where does the weather go? How does it go around the buildings? What do you lose sight of? And so I just want to put this vocabulary of digital twins, and then you can simulate disasters. And obviously they use it for training of pilots and so on, but it's getting much more interesting, I think, in the last 10 years. So, okay, Dave, I'm going to hang up on you because I've got
that's fine. Thanks very much.
So.
Thanks a lot, Roger. Take care.
Okay, very good. Bye-bye.
So I'll make a comment about digital twins and what Roger said. No, what Roger said, and if you can add Canada geese to those, you're really doing people a favor around airports. They are the most dangerous bird by a long shot. Anyway, so Pete, before moving on to another question, what did ENS find out about photorealistic images in its work with simulators?
We started out doing very, very basic texture capabilities, I think with CT6 as our product line evolved. And originally, texture maps were just large memory hogs that could store generic or specific imagery. We applied MIP texture to make resolution pyramids. We innovated in one of those slides, what's it called? Anisotropic texture filtering that I think I invented, which allowed you to selectively filter the texture when it's rendered so that the down range pixel densities and the cross range pixel densities are accounted for properly, so the texture doesn't just wink at you. Later on, we started using photo texture on vertical objects and making, as I'm sure you've seen in lots of computer graphics work since, fanfold trees and photographic texture that is used on geotypical items and then replicated all over the place where the underlying texture memory is used more efficiently. So photo texture had a big outburst from us once we decided to put texture in the image generator and apply texture to polygons, whether they were runway polygons or trees or the sides of buildings or even sky cloud patterns or the rough marks on a runway. So as time went on, texture got used more and more, and it became so challenging to store lots of photo-specific texture and to page it into active memory because you're flying around seeing different specific and generic texture patterns all over the place across the terrain, and you have to be able to manage what set of textures do I need right now, which of them are generic and can be applied in a replicated sort of way to the 3D models before the rendering is launched, and how much sort of geotypical texture is needed for the geotypical themal technology that I talked about.
Did pilots, as you evaluated their performance, do better with highly photorealistic environments, or was non-photorealism okay?
I don't remember that we ever evaluated that specifically, but our tendency was to use specific texture patterns, whether they're very specific to a location or specific to a certain class of or type of objects. We tended to use very specific textures we borrowed from photos and then applied very carefully across the total database. And as far as I know, pilots texture is occasionally texture is a critical visual cue to make a control action on the airplane. But in a lot of cases, at least in my opinion, texture is a rich background thing that creates optical flow that gives the pilot a very strong sense of being oriented, of being generally in a place or near a set of things, But to answer your question fully, I'm not sure we know.
Okay, that's a fair answer. There's a
good answer. I mean, a good question.
Julian, go.
Yeah, speaking as a pilot, I would say a lot of times I'm using geometry as cues. For example, just before touchdown, I'm looking at the relative angles of the edges of the pavement, the runway pavement, to judge what's going on. And I'm not looking at the asphalt texture or whatever the pavement texture is, but where the lines of convergence are. So.
Got it. So there's a classic book, just as kind of a reference, called Perception of the Visual World by Gibson. It was published in 1950. If you get a chance to take a look at that book in terms of answering how pilots work, Gibson studied the people he studied were primarily Navy pilots who knew how to land on aircraft carriers. If you think about that as a problem, it's non-trivial. Anyway, so I'm going to flip something to you, Julian. How are budget cuts influencing visualization work?
Well, from what I can see pretty seriously, I know that the group that replaced or took over from the graphics lab was seriously decimated not too long ago, and I would imagine it's even more decimated now. So, if it still even exists. My suspicion is that the current administration is planning to let fans do the visualization.
Oh, crowdsourcing visualization? Is that what you're suggesting?
Yeah.
Okay. You never know. So another question for you, Pete. What do you remember ENS having a hang glider at SIGGRAPH back a number of years ago?
I think so, but I can't remember very well.
Do you have a clue as to when that happened? Because I sure don't. I remember the demo.
I'm very rusty here, but as ENS sort of penetrated the airlines and military markets, we spent several years in some major sorties, believe it or not, into the entertainment world. And among other things, as I remember, we made a hang gliding simulation.
Yeah. Oh, yeah.
Also made a dragon simulation and a bunch of other stuff that was sort of entertainment focused.
Mid-90s, one of the LA SIGGRAPHs.
That could be.
If anybody in the audience, Joan, Abilene is a little too young for that. Joan or Ed or Leonard, if you have an answer, please put it in the chat and I'll refer to it. So here's another question. This is a question for the panel that I thought was pretty interesting, and that is, you've seen how our work has led to today's technology. How would you like to see the technology go in the future?
So much of the work that we've done in real-time simulation and all the recent developments that we, sampled lightly in my talk, deal with the focus on training. And none of this technology has been contemplated for socially redeeming content, such as you see in games. And if this is really pretty wild, but if I were king for a day, it would be lovely if this kind of training simulation, appropriately focused on different kinds of models, could teach people how to get along in the world.
Julian, any comments?
Yeah, I want to wholeheartedly agree with Pete. And my very viewpoint is that we have all this technology available, is that we should use it to see or to try to understand what we can't see, what we can't experience. For example, one of the things that happened with the advent of computational physics was more study in chaos theory. And if you're familiar with chaotic attractors, you know that they can't be seen because they're in a phase space, and phase spaces only exist as a conceptual kind of thing, but they help you understand what's going on. And in the same way, there's so much that is going on that could help us understand if we could just see it somehow. And that's where I think the technology could come in, is to leverage the human experience, not just enable it.
I agree, Vladimir.
So we're in violent agreement here. Let me add a little bit more. Well, somebody's got to be violent in this group. It can't be all peaceful, right? Anyway, at any rate, so one of the things that I've observed about my work with SIGGRAPH over the decades, and it's been a long time, is that computer graphics is a universal sort of form of technology. And if you start parsing through the applications of computer graphics and where it has gone and it is going, it has diverged significantly from previous generations. Honestly, it's all about the data. If you start realizing, as a person who is involved in arts, entertainment, aerospace, dentistry, for God's sakes, medicine, all of the architecture, all of the data ultimately turns out to be mathematical forms that allow you to model what you think is reality into something that is useful. I would love that we find a forum, either at SIGGRAPH or in some other place, that we can start having these communities talk to one another, because there is mutual benefit of people understanding that all of these things can in fact work together. Julian made a really good point about computer-aided analysis and engineering changing the way that you actually wind up doing business as an engineer. All of the disciplines in engineering are codependent, and sometimes they actually talk to one another, although not frequently. So that's one piece. The other part about the data is that data tends to be less than accurate as we human beings define it and work with it. That impacts our ability to use it in downstream processes, number one. So it's hard to assemble a commercial airplane when the data is incorrect and you write work instructions that are based on incorrect data. So you have to go back and fix it and eventually get the data correct enough that it allows a flying object to occur. It also impacts all of the training and what we're doing for the joy of artificial intelligence, or other techniques that try to optimize how we deal with complex systems. Because in reality, we're building complex systems and we're not going to get out of that business. That's what humans are remarkably good at. So so data and interaction amongst disciplines that use our field would be wonderfully helpful, in my opinion. So we haven't answered Ed, thanks to Ed Kramer. Ed Kramer, my friend, has noted that the virtual glider occurred in 1993 and in Anaheim. So you get partial credit, Julian.
What do you mean? Anaheim is LA.
Huh?
I said LA and Anaheim
That's
is
why I
LA.
said no, but you didn't know the year.
Oh,
Partial credit, so Jeopardy would have kicked you out of there, man.
yeah. 2 years different. 2 years difference is still one standard deviation.
Oh, doesn't work. Anyway, so here's another question that I think you get this one, Julian, because you actually participated in this. How does one join the team that makes 3D animations for NASA or JPL?
Oh, well, that goes back to a question from a couple minutes ago, which is that I don't know if there is a team anymore. And I saw a commentary that the guy I knew who was in that group was laid off. So it may not be possible anymore. So
Great. Great. All right. Anyway, so sorry we can't give you a better answer, Keith. So we get another in sharing our experiences. So for people who there are resources, as Julian has pointed out, for computerhistoryinstitute.org in providing computer graphics history. There are publications. The Annals of Computing History is in the process of publishing 2 special issues on computer-aided design, the history of computer-aided design. There is a lovely set of columns in computer graphics and applications called Origins of Visual Computing that talks about the history of what people have on people's real experiences that range from contributions from Turner Whitted and Pat Hanrahan and Ed Catmull about the origins of RenderMan. Lauren Carpenter will have an interview later this year. Some really nice stuff. And if you want some light reading, I'll show you a book here. It's called A New History of Modern Computing, written by Thomas Hay, H-I-G-H, and Paul Ceruzzi. I'm working my way through it. There are some wonderful stories about how computing and computing machinery actually started and became so dominant today. And it's not even too boring a read. So that's another recommendation. A whole bunch of stuff that people can rely on to get a better sense of the history of this field. One last question that is written here. The animation and visual effects industry owe a lot to our field's visualization research. Were you inspired by the CG imagery you experienced in films? I've been uninspired by some of the CG imagery, but mostly inspired, especially when there's a really good story associated with the imagery. Because in point of fact, certainly it's my feeling that the way you may bring value to imagery is by having a story associated with it, in film especially. From a professional perspective, working at a research lab and for the automotive industry and in the aerospace industry, I was motivated professionally far more by being able to let people interact with my imagery, with their own imagery. And it was my purpose in life to make it as easy as possible so that they could understand their own data. It was their story, not my story. So that's how I got involved. And their imagery, quite honestly, looking at it and being able to wander through the bellies of airplanes was extremely inspiring to me. And it became even more inspiring when I got to walk around Boeing assembly factories and see the darn things being built, and you realize, how did we ever figure this out? Anyway, Julian, any comments?
Well, I'm such an old man that there wasn't any CG in films when I started. It was just Westworld had the only CG, and I didn't even get to the original movie, right? I didn't even get to see that. As far as being inspired by CG in films, me and Jim were making films, and we had the background from conventional animation to work from. So I think what eventually inspired me was at Ohio State was seeing all these animators using this oncoming technology to tell stories. Because like you said a minute ago, it's about story. And that was inspiring.
I would love to see very realistic, extremely responsive, interactive graphics applied to social life and sharing of stories by putting people in situations where they're in the moral crux or they're in the fight or flight moment or whatever it is, you know. And I'm sure you can make up a lot of examples, and I don't know what that means for the technology or the realism of the graphics or what. But when I look at CG movies, you know, a lot of it's just incredible models flying around in somewhat meaningless ways that do serve a story, but they're not personal. And I'd like to see computer graphics used to make highly interactive, socially aware, immersive experiences for people to share stories.
Yeah, so
and to learn social skills and insights from such encounters.
learning is a really good thing, and that constraint of being able to interact in real time is a real differentiator between what happened in certainly in my career on how do you actually get these things to how do you actually get people to work and understand their own data in an interactive session is a really big deal. I admire what happens in the arts and entertainment world. It's unbelievable what people are doing. Ironically, much of the content is being developed with interactive systems. And Pete's point about trying to let people get involved with the story, I think would be a very interesting thing to do. Anyway, we'll take one more question, and it's from Kyle. I am very interested in data representation and knowledge navigation, especially in the area of orthopedic surgery. If there are others interested in this area, and let me tell you, Kyle, I'm interested because my knee's getting replaced next month. So any comments on those data representations for orthopedic, for medicine, and it happens in dentistry now too. Any comments?
I can pity you, feel sorry for you getting your knee replaced, but orthopedics is completely out of my area.
This is not my area either, but it so happens that an old friend from E&S jumped ship and went into medical graphics. And one story he told me at the picnic a couple weeks ago, and I wished I could reconstruct it, but it involved helping a surgeon and live x-rays, maybe fluoroscopic stuff, taken in during surgery, make tactical decisions about surgery based on, x-ray or fluoroscopy assessments of live surgical risks and opportunities. And I can't reconstruct the story of what the underlying technology was, but the guy was having a ball talking about getting that kind of live assistance to surgery on bones in this case through the the Food and Drug Administration approvals and all of that in order to actually go live. Anybody know what that is?
Well, so there's a device called a Mako device that allows you to do that. And if you've ever had heart surgery, it's all guided by cameras and robotic assists. I'll conclude with one last story before turning it back over to Abilene and Joan. And that is, I have a daughter who works in the orthopedic business. Her comment was that when she heard I had to have my knee replaced, that surgeons about 10 to 15 years ago were really happy when they splattered blood on the walls because it was such a manually intensive task. Current knee replacement is done mostly robotically with a robot doing the cutting and getting guided. It's far less barbaric. Anyway, with that, I'll turn it over to Joan and Abilene for some last comments.
Yeah, there's a comment for you. Hey, but between Pete and Julian, I was curious as to what you two really thought was the first time we started using the term real time. I know I expected it to be Evans and Sutherland, but was it the PS2 was the first thing doing real time, or what do you two think? Or the
So
first time you started calling it that?
I know with the PS2 we called it real time, but then being at NASA, I started dealing more and more with the Department of Defense, who actually had a definition for real time and discovered that what we were calling real time really should have just been called interactive. And I also discovered that just about all salespeople from all 3D workstation companies would use the word real time when they should have been using the word interactive, at least according to the DoD. So
As early as the first half of the 60s, people were talking about real time as the experience of instruments or ground plane textures or something, which were the earliest manifestations of real-time visual simulation. And the understanding was if you were in real time, you were in the experience. And no matter where you piloted, the world reacted to you as if you were there. And real time meant keeping up with events and your own behaviors as you adjusted your viewpoint and aim angles. And I think that kind of terminology was probably used in the early mid 60s.
The notion of human computer interaction is a really big deal. It's not just frame rate. It's responding to a person in under a quarter second or less. And that includes things like controlling movement and controlling motion. And that's been around for a long time.
When you look at a total simulator, it has a so-called host computer that has a model of the dynamics of the aircraft and all of the instruments and other, deployable surfaces and things on an airplane. And that computer, from the time it receives control inputs from the controls that are, wired in a simulator cab, it has to come up with a dynamics reaction to however the pilot has changed the controls and forward its belief about where the airplane is onto the visual. And then the visual may have 2 or 3 frames or fields of further delay walking through the environmental processing and rendering steps to get out of the frame buffer and finally into a pixel stream. And that total lag, if it's more than a few frames, it's possible that the pilot will go into control oscillations and wipe out. So
thanks for that knowledge.
So being in real time means not just tracking, the simulated aircraft behavior, but presenting it quickly enough that you don't go into a over control situation. So there's tremendous pressure to reduce that total system lag from a control change to a pixel, down to some tolerable level. And there have probably been scientific studies on that, but I just know that more than a few fields or frames of total delay through that thing is not tolerable. So that's part of, what simulator companies are trying to deal with.
Thank you to all the speakers and presenters and everybody on the tech crew and everybody that, volunteers for LA SIGGRAPH. I think this will do it for us for LA SIGGRAPH and the SIGGRAPH pioneers on this event. We operate entirely on contributions from members. Please consider joining our chapter or donating to la.siggraph.org. And remember, you can become a member of the pioneers. Ed Kramer will help you. So thank you all again. And that would be our good night.